Okay, last one for today. Let's say we have a thing called an Atwood machine. Maybe you've seen this before, or maybe you've seen one demonstrated before. You might have, you probably have, but you may not know it was called an Atwood machine. Atwood machines are a pretty simple device. We have a table, horizontal table. We have a pulley system. We have a mass on that table, and it's connected through a string or rope or something to another mass. And this is a hanging mass, just hangs there. And if I let this thing go and I release it from rest, it will maybe accelerate or hang or, do several things, depending on what the physical situation is. So here, the physical situation that we have is mass 1 is equal to 300 grams, mu sub k is equal to 0.7, and this is the mu sub k for M1. There's no surface interaction for M2, so we don't have one. The distance from where this thing starts until the ground is 0.75 meters. We'll call that delta y2. And then we want to know what mass, if I were to hang it on there, what mass M2 would give me a final velocity of square root 3 meters per second after traveling a distance of 0.75 meters directly down. So this is a pretty rough thing to think about, conceptually. It's just about as rough to actually do. It takes quite a bit of thought and careful planning and analysis and patience as well. So let's start off talking about the first mass. Actually, let's start off talking about our direction. I'm going to say for object number 1, let's look at that mass number 1. I'll say that to the right is positive x and to the up is positive y. Now, if I place my fingers, say right here on this rope, on this or string or whatever, and I point in the positive direction and I follow that string, that needs to continue to be my positive direction. So here's me following it here in this direction, but then I go over this curve and this way, and now that for my mass 2 down has to be my positive y for mass 2. So we're giving each object a separate coordinate system, but they have to agree. And in fact, I'm not even going to call that my plus y. I'm going to call that down for mass 2. I'm going to give its coordinate system, I'm going to call that a plus x. You might say, why would down be plus x for just that one object? Well, it makes sense, right? Because it's positive x to the right for mass 1, and if I keep following that string down, then it still is pointed in the positive x direction. It's kind of like taking my whole thing, grabbing that mass 2 and then straightening it out into a horizontal line and pulling on it with the same amount of force as it would be with holding, letting mass 2 hang and let gravity pull the whole system. So these are exactly the same motion as far as physics is concerned. If I have mass 1 and it's on this horizontal surface and I now pull on it with the same force as it would get from me hanging mass 2 on the end, then I would still have the same acceleration, the same thing that I'd have to consider. But the thing is, we're replacing that pull force now with this gravitational force, or this reduced gravitational force that you'll see here in a little bit. So there's a lot going on here. There's tons and tons of stuff to really unpack. And the first thing that I would look at when I think about this is this thing going to move? And the answer is yes, it's going to move. It tells us that it's going to move because it gives us an initial velocity of 0 and a final velocity that's not 0. So it has to move. Our final velocity and our initial velocity are telling us something. It's telling us that there's a change in velocity and therefore there is an acceleration in the y direction. So my first step on this, my first step would be to draw free body diagrams for both objects. But my second step would be to calculate that acceleration. Let's go ahead and take a second and draw those free body diagrams. So I'll put mass 1 on the left and mass number 2 on the right. So go ahead, take a second, try to draw those free body diagrams, and we'll check in just a moment. Okay, so you should have had a chance to draw some free body diagrams. For mass number 1, we'll say that this direction will be our normal force. This will be our force of gravity. They cancel each other out. We will have a friction force backwards, F sub k, and we will have a forward pointing tension force. It points to the positive x direction. On the object number 1, or mass number 2, I will not have a tension force pointed left or right. It's actually going to be pulling my mass up. because of Newton's third law, right? So Newton's third law says that the tension force that the mass 2 exerts on mass 1 is equal to the tension force that mass 1 exerts on mass 2. We also said that for mass 2, this down is the positive x direction. So our tension force is not pointing in the positive x direction for my mass 1, and through Newton's third law, we could say that it points in the negative x direction for mass 2. The tension force is also going to have a gravity force acting against it, and it's going to be bigger than our tension force. It has to be bigger than our tension force, otherwise there's not going to be an acceleration down. So that's our free body diagram picture. We still have a lot of work to do to get to this whole situation, but I want to start the actual mathematical portion of this. So maybe we can do it up here. All right, so the mathematical part, first thing we know is that it's going to fall. Mass 2 is going to fall, but it's not going to fall with the acceleration of 10 meters per second. It's got that tension force. That tension force is going to eat up a lot of that 10 meters per second from G, and it's going to leave something else left over. How do we find that? Well, since we are being accelerated by gravity, we should know that that is a constant acceleration. Gravity doesn't really change much near the surface of the Earth, so G is roughly constant. Constant acceleration, as you remember from last unit, means we can use kinematic equations. Specifically, we can use V final squared is equal to V initial squared plus 2 times A times delta x, right? This is delta x, and we're talking about mass 2 here. We're talking about mass 2 because mass 2 is really the force of gravity acting on mass 2 is going to be what drives the system. So we'll start here looking at it, at the driving force. Velocity initial is 0, so we'll get V final is equal to, or V final squared is equal to 2a times delta x. Delta x is going to be a positive value because we're going to get pulled down by gravity. So it moves in what we're calling the positive x direction for mass 2. And so delta x is a positive value. Acceleration will also be a positive value in the x direction. And our velocity final, we've already been told that that's positive, so it points down as well. So I can solve this for my acceleration by dividing both sides by 2 delta x, and I get V final squared over 2 times delta x is equal to my acceleration. I know what my V final squared is. That is square root of 3. Let me add units to square root of 3 meters per second. That gets squared, and I divide that by 2 times delta x, which is that 0.75 meters that the object 2 will fall, or mass 2 will fall. Plugging this into a calculator, I can see I get square root 3 squared. That's going to be 3. I divide that by 2, and I divide that by 0.75. So basically, I'm taking 3 divided by 1.5, which is just half of 3, so I get 2. Just to be clear about that, let's say we get 3, and our units are meters squared over seconds squared, and we're dividing that by 1.5 meters, and so I will get 3 divided by half of 3, so or I can call it 2 times 1.5 divided by 1.5. Those cancel, and I get 2. So my answer for that, for the acceleration, will be 2 in our units. Well, we have a meter on the bottom, a meter squared on the top, and those cancel. Well, one of those on the top gets canceled by the one on the bottom. I'm left with 2 meters per second squared, which is a acceleration, or units of acceleration, and we're pretty good for that. Okay, so now that we've calculated our acceleration, and I did that for you, go ahead and try to set up a Newton's second law situation for our masses number 1 and 2. I will start you off by saying that the sum of forces in the x direction on mass 1 is going to be equal to mass 1 times acceleration 1, and the sum of forces on mass 2 is going to be equal to m2 times acceleration on object 2. Again, this is a vector equation, so go ahead and make this, split up your sum of forces for each thing, and then change it from a vector to a scalar equation, and we will see you in just a second. Okay, so we have 2 sums that we're dealing with, and these are just the x direction sums. We also have a y direction sum on object 1 that we'll have to deal with. But the forces acting in the x direction are going to be the friction force, the kinetic friction force on 1, plus the tension force. And that should give us m1, a1, and those are vectors. For forces on object 2, don't like that. Forces on object 2, we are in the x direction. We are going to have a force of gravity vector plus a tension vector. And that will give us m2, a2 vector. Sorry, that's kind of hard to see. We should know something about objects that are connected. They accelerate at the same rate as long as that tension doesn't go slack. And it's not going to go slack while we're hanging a mass from another mass. When we have that second mass hanging, once that tension reaches, it's not going to, or once that tension is there and that string is taut, it's not going to stop that until the bottom mass hits the ground and, loses that gravity force, because the normal force cancels it out on the mass 2. So what we should know is that our acceleration of 1 is equal to acceleration 2. And I can do that and plug those things in to maybe just call it acceleration A. And we can go from the vector world to the scalar world by saying our tension force on number 1 minus our kinetic friction force on 1 is equal to m1 times A. And we also get our gravity force for object 2. Our gravity force on 2 minus our tension force is equal to m2 times A. So let's go ahead and get a new page because we're running out of room here. I'll pull that over and I'll copy over our things, our equations that say that is that our friction force, kinetic friction on 1, is negative. We add to that T and we'll get M1A. And then we have another sum of forces that is force of gravity acting on object 2 minus that same tension force is equal to M2 times A. Okay, so we're doing good. We've got some simplification going. Things are getting a little bit easier to deal with. You might see that we have two equations and we have this tension force that we don't know and this acceleration that we don't know. That's great, but still kind of maybe a little difficult to deal with. So let's do one more force sum. And we're going to need that because we have a friction force. So when you have a friction force, you need to know what the normal force is. So let's calculate our normal force. Over here, I will write the sum of forces in the y direction on object 1 is equal to 0. So that is a Newton's first law statement. These two are Newton's second law statements. And the sum of forces acting in the y direction on 1, well, that's going to be a normal force vector plus the gravity force vector on 1, and that will give us a 0. And these are vector equations. Normal force will point in the positive y direction, gravity on 1 points in the negative y direction, and so if we do this n minus fg1, we'll get 0. This tells us that our normal force is equal to the gravity force on 1, which is just m1 times g. And that's kind of what we would expect, right? So now we have an expression for normal force, and then these two other sums, and we still got so much work ahead of us. But the next thing that I want you to do is take this equation and take this equation and try to solve them both for the tension. And while you're doing that, go ahead and replace things like your force of gravity and your friction force with their respective equations that you get from the very beginning of this unit. So I'll give you a moment to give that a shot, and when we get back, we'll talk about it. All right. So hopefully you got your equation set up. Solving it for T for the mass 1, I get T is equal to, or tension is equal to M1A plus the friction force Fk1. And then plugging in for my friction force gives me M1A plus mu K times N1. Once again, we'll substitute in our normal force, which we found over here, and I get that tension force is equal to M1A plus mu K times normal force, which is M1 times G. So my tension force has to be equal to my my friction force plus the extra amount of force that I would need to reach acceleration A, and that's kind of what we should expect. On the other side, on the mass 2 side of things, I can solve this for tension and get tension is equal to my force of gravity acting on object 2 minus m2 times a. And that makes sense because what we're having is the force of gravity is, and we saw the acceleration is going to be 2, right? It's 2 meters per second squared. So force of gravity is where we started out with 10 meters per second squared, and then we remove this amount of force to bring it down into from 10 to 2 meters per second squared for our acceleration. Replacing that those equations gives me FG2, that is m2 times g, and then I subtract my m2 times a. Maybe I can factor something out like an m2, again m2 times g minus a. And here in this parentheses, we see a statement that this force is the difference that, or this force is what causes, this tension force is what causes our difference between g and the acceleration that we actually experience a. Again, that's at 2 meters per second squared. Okay, so a lot of talking done. We figured out our tension force for both of these things. So now I'm going to tell you we have two equations. This will be equation 1, and this will be equation 2 for mass 1 and 2. And we have two equations, and we have two unknowns. So I'm going to write out a statement that says about, the statement comes from math, and the statement says, if you have two unknowns, you will need at minimum, two equations to solve for your unknowns. Here we have two unknowns, tension, write a list of them, unknowns. You have tension, and you don't know tension, and you don't know mass number 2. But you also have two equations, which are going to allow us to solve for those two unknowns. So you're going to have to do something mathy, and I'm going to let you figure out what that is. I'll give you a few seconds, maybe pause the video, try to work it out. But if you can't get it, whatever, I will give you a solution here in a second. Okay, so you should have a solution. If not, no big deal. This one's kind of rough. But the thing is, I know an expression for tension, T, it's this m1a plus mu k m1g. I have another expression, it's this. If T is equal to both of those expressions, this is one of those situations where we have A is equal to B, and if B is equal to C, then A has to be equal to C, right? So if I have T, maybe I have A is equal to T and T is equal to C, then that tells me that this A and this C have to be equal to each other. So let's go ahead and write that out. I will have I'm getting a little freezy. There we go. I will have m1a1 or m1a plus mu k times m1g is equal to m2 times g minus a. And this is again, saying that my tension is equal to both of these, so I can set these equal to each other. Okay, next thing, I need to solve this thing for m2, but I'm going to make the left side look a little bit neater. I'm going to say factor out an m1, and I will get a plus mu k times g times m1, and that will be equal to m2 times g minus a. Okay, so from here, you should be able to figure out how to calculate the rest of it. I will give you the solution in just a moment, but go ahead and try to work it out. We are trying to solve for the mass that will give us an acceleration such that at the bottom of the motion, the final velocity will be square root 2, and you fall in 0.75 meters. So go ahead and give it a shot. Okay, so maybe you figured it out. You should have gotten the answer that the mass is going to be 0.3375 gram or kilograms. We could also call it 337.5 grams if we wanted something like that. That would be our answer. But how did we get there? Well, we divide both sides of this equation by g minus a. G minus a's cancel, and what I get is my mass 2 is equal to m1 times a plus mu k times g divided by g minus a. We know g is 10 and a is 2, and so on the bottom we get an 8. On the top we'd have 0.3, the mass of mass 1, times a plus mu k times g, and that ends up being like 9. So if I plug all this in my calculator, I should get somewhere around m2 is equal to 0.3375, and units will be kilograms. So there you have it. Atwood machine. We can, now that we know what that mass 2 is, we can now calculate what our tension force is too. So a lot of times as a second step or third step or whatever, how many steps we're at, it's to calculate the tension. So what I want you to do now is go ahead and calculate that tension. I'll give you a few minutes to give it a shot and come up with an answer. All right. So I've gotten the information that we need on another page, so we got some space to work. But we have an equation that gives us our tension from the previous set of stuff we did, and that was tension is equal to mass 2 times G minus A. We know G, we know A, and we can and we just found what M2 is, so I can calculate M2. I can calculate T by taking my mass 2 in kilograms, 0.3375 kg, times my gravitational acceleration constant, 10 meters per second squared, minus my acceleration that I experience, which is 2 meters per second squared. And then if I plug this into a calculator, I should get my result, which is about 2.7 newtons. The tension in the string is 2.7 newtons. Let's go ahead and look all the way back to the beginning right here where we started out, and all we knew was the distance this thing fell for, the mass of object 1, a coefficient of friction, and a final velocity. So this is not very much information, but we were able to figure out the acceleration of the object using kinematics, use that acceleration and understanding that the acceleration for mass 1 and mass 2 will be the same. We used Newton's second law, and we were able to calculate or find an expression for tension for both masses. And then we set those expressions equal to each other because tension should be equal to each other in that string. Then we used our mathematical knowledge to state that there are two unknowns and two equations, and so we had to use what we call substitution or elimination to get rid of that tension by setting those two equations equal to each other and then solving it algebraically for mass 2. Once we have that solved, we can plug some stuff in, we get our mass number 2. Then we're asked to find the tension. So we just went back to one of our equations that we found. We used the simplest one, which is the M2 times G minus A. Because all I have to do is take 0.3375 and multiply it by 10 minus 2, or times 8. And what I get for my answer then is that 2.7 newtons of tension in the string. So all that work, lots and lots of time, lots and lots of effort, but it's a pretty interesting problem, and we'll probably see more of those. I can pretty much guarantee that you'll probably see an Atwood machine on the AP exam. So just so you know, but otherwise, I hope you guys have a good day, and we will see you later.